Great. So I'm thrilled to introduce Jayadev Athreya, who's a professor of mathematics and comparative history of ideas at the University of Washington in Seattle. He's also the co-director of the Pacific Institute of Mathematics and the founder of the Washington Experimental Math Lab. He's also an artist. He's exhibited work at the Center for Contemporary Art in Seattle. And on a personal note, Jayadev hired me to manage the makerspace at the Washington Experimental Math Lab when I was a graduate student. And this job really jump-started the way I think about and integrate mathematical illustration into my own work. And I can honestly say it completely altered my career trajectory in a good way. So I'm really excited to introduce Jayadev today.
Um, Thank you for that incredibly kind introduction. And if that's like my entire contribution to this community, that's a huge one. If I got Gabriel even a little bit up and running on this, I take that as a huge, huge positive. It's wonderful to be part of this community. I know today, it's been a tough week for many of us, and mathematics doesn't live outside of the real world that we live in. However, I think one of the things we've all been thinking about, hopefully, is how to act locally to build communities and support each other. And I don't think it's being exaggerating when I think that this community can be a fantastic support and source of joy for many of us. So I hope it can continue to be that going forward. Um, okay, so today I'm going to show you a bunch of pictures. Include many like the slightly psychedelic one behind me. This is created by my wonderful co-author, Pat Hooper. I'm going to try and explain what is some of the mathematics behind some of those pictures, and then throw out some challenges for illustrating some of those mathematical concepts, maybe beyond some of the pictures I show you. Stuff I would love to brainstorm with this community about in the near or more distant future, whether that be at ICERM in August or at IHP next winter. I see also, thank you. I see Sylvie is here. Thank you, Sylvie, for hosting us at IHP. In fact, I'm in Paris, and tomorrow I'm going to swing by the Maison Henri Poincaré, which I'm very excited about to see tomorrow morning. I also see Pierre Arnoux is here. Pierre, you're going to see some pictures that you made uh, 35 years ago now at the end of this talk, as part of some of the challenges that we want to throw out to folks here, or the ideas here. Okay, so without further ado, let me just start showing you some pictures. I'm going to first show you pictures without kind of any explanation, just because I think they're cool. Like I said, all of these pictures are created by my colleague, Pat Hooper. All of this is based on joint work with Nicolas Betterid, Pat Hooper, and Pascal Hubert. Okay. So picture number one, which I think is pretty cool. To me, it looks like, one of those old style television network logos or something like that. This is a 20-gon, by the way. So this is not a circle. It's a regular 20-gon. Um, this is a staircase, which is, I will tell you, is related to a 7-gon or a double 7-gon. And I'll explain what that related means. This is another sort of function on that staircase. And this is a 3D print whose base is a 7-gon again, and is again related to those previous pictures in a way that hopefully I'll be able to explain by the end of the talk. This again is made by Pat. There's in fact two pieces of it. There's a red piece, which I unfortunately don't have a picture of, and they fit together in a very satisfying way. I don't have those prints with me, but if anyone is interested in those STL files, I have those and wants to make this print. Okay. Maybe the first thing I'll ask before I go into the talk is, do these pictures, I mean, has anybody seen things like these pictures before? If so, please let me know in the chat or in the Discord, because I've seen certainly things somewhat like it, but it's always nice to see what other things these pictures trigger. And in fact, these pictures came before some of the theorems we proved. And in fact, our theorems were guided often by these pictures. So this is again a case where illustration really helped us understand what it is we were trying to prove and what we should be proving. It's not just a case of we proved something and then we wanted to make pictures. It's we made pictures and we made computer experiments, and that really helped us figure out what it is we needed to prove. Okay, so now let me start by asking a very, very general and way too hard question, which is, what can we say about billiards in polyhedra? Now, let me first justify to you why I think that's too hard a question in complete generality, because this is already a question that's too hard in full generality. What can we say about billiards and polygons? And when I say what can we say, I mean, can we sort of completely understand all trajectories, for example? We start with some polygon, we start with some point mass moving around and points in a certain direction. Can we say what it's going to do? Will it come back to where it started? Will it sort of spread out evenly? In fact, even if we just restrict to the simplest polygons, triangles, I want to first tell you that we know very, very little. I want to try and convince you that this is a subject in which we know a lot about a certain class of examples, but we know extremely little in general. So first of all, let me tell you what we mean by billiards. We're mathematicians here, so we're going to eliminate a lot of complications. We're going to say we have a point mass moving at unit speed, one point mass. We're just going to have one billiard ball bouncing around this table. It has no friction, and we're going to have elastic collisions with a wall. So the angle of incidence equals angle of deflection. In particular, once I get started, and as long as I don't run into a corner, I kind of can continue my trajectory forever. The trajectories that run into a corner form a kind of measure zero set of trajectories, so we're going to ignore them for right now. They are very interesting. For instance, trajectories starting at one corner and finishing in another are very interesting. They're called generalized diagonals, and that's a subject of a different talk. But one question you could ask, for instance, is, are there periodic trajectories? And another question, which is going to be much more the focus of most of this talk, is how do long non-periodic trajectories behave? Okay. But let me first start by saying a few words about periodic trajectories, because this is a great way of illustrating how little we actually know about general billiards. So if you get bored, I strongly recommend you do the first exercise. All acute triangles have a periodic billiard trajectory. And in fact, there's a hint on the previous page, right? This is an image stolen from Quanta magazine. They had a nice article about billiards, and that picture is kind of a hint as to how to do the first exercise. If you have a triangle, which is acute, that is all angles are less than 90 degrees, then there is a periodic billiard trajectory. And in some sense, this is an exercise you can do using high school Euclidean geometry. Much harder is that every obtuse triangle with obtuse angle at most 100 degrees has a periodic path, has a periodic billiard path. This is the theorem of Rich-Schwartz from 2006 with aid of computation and illustration. In particular, I want to point out this amazing program that Rich and Pat Hooper created called McBilliards, which helps you explore periodic billiard trajectory. There's a link in there, which I don't know, I can see if I can drop into the, oh, that's not, okay. I'm not going to try and copy and paste in real time. You can, if you Google McBilliards, this pops up. It's a really fun program to play with. It investigates sort of the combinatorics of billiard trajectories, and using that, and using, again, informed by illustration and experiment, Rich proved this theorem. That's been extended now to 112.3. I believe that's the current record. Students were involved in this. This is Tokarski, Garber, Marinov, and Moore from 2018, and again, using computation. And it's still completely open for general obtuse triangles. So, it's funny, right? You take a physics class, an intro physics class, and you do Newtonian mechanics and electricity and magnetism. And you're like, yeah, we kind of know everything. It's like, no, this is incredibly simple Newtonian mechanical problem that we don't know the answer to. So, having told you we know nothing, now let me tell you some class of polygons that we maybe know more about. And these are going to be called rational polygons. So this title of the slide is Under the Streetlight, because I always make this joke about, we are kind of the people scrabbling around looking for our keys under the streetlight, and someone comes and asks us, did you lose your keys over here? No, we lost them over there, but the light is much better over here. So we might be interested in the completely general problem about billiards, but we have a lot more machinery, have a really powerful streetlight here when we think about rational billiards. So what are rational billiards? The name comes from the fact that you can think of these as polygons, all of whose angles are rational multiples of pi. But as a geometer, it's maybe a little bit easier to think about this by saying that when I do reflections in the sides, the group modulo translations, of course, we're going to get a lot of translations when we consider the group generated by reflections in the sides. But modulo translations, this group is going to be finite. Equivalently, you could think about all the sides of the polygon, if you think about them extending them as lines to the origin, and considering the group generated by reflections in that should be finite. all of these characterizations. And here's a picture, which I'm not really going to, I'm going to try and show you a little video, which does it in a much simpler case of a rectangle. But here's a little video of a process that you can do to going from playing billiards, and this is a little an interesting little kite kind of shape, or maybe I don't know, this is a dart, I guess. And you reflect it, and you do reflect it a bunch of times, and eventually you stop doing these reflections once you get, you know, sort of the full reflection group in these lines through the origin, and then you get a shape in which every parallel side has a parallel friend of the same length, which you can identify by translation, and that object is called a translation surface. Okay, I don't want to go write down a full precise definition again. It's just a place where I want for this, I want, it's a place where you can play Pac-Man. It's maybe a complicated place where you can play Pac-Man. Every time you go off a side, you can come up another side going in exactly the same direction because you've glued these parallel sides of the same length. So you can do flat geometry on this surface. There might be some points of singularity where the angle is bigger than there's points with cone angle bigger than 2 pi. In fact, this surface will have quite a few of those. The one that's drawn here, again, this is taken from that nice Quantum Magazine article, which I highly recommend. Um, but the point is you can just get this nice surface. And on this surface, the billiard flow on your original polygon turns into this Pac-Man flow, this straight line flow on this surface. So if you bounce around on the billiard, that corresponds to just unfolding and going straight and then following through identifications on this surface. So again, let me say those, you know, now having said it once, let me say it again with text. When a ball hits the side of the polygon, reflect over the side. So build a new copy of your polygon, reflected over that side. Get several copies indexed by this group of your polygon, where now each side in each copy has a unique parallel friend of the same length it is identified with by translation. And then the resulting object is what we're going to call a translation surface. It's a compact surface. In fact, since translations are holomorphic, it's a compact Riemann surface. And since DZ is preserved by translations, it's a compact Riemann surface together with a holomorphic one form. You don't need to know what any of those words are. I just wanted to say that for folks who like to think in complex analytic or maybe an algebra geometric kind of language, is you're building an object with lots and lots and lots of structure. I should say this unfolding construction is very old, and it's been found by many groups of people in many different places. The first recorded published version I know is by Fox and Kirshner in the 1930s. Fox, of course, is famous topologist. They wrote this when they were master students. These are pictures of them from much later in their career. Kirshner went on actually to become a rocket scientist. He worked at Johns Hopkins Applied Propulsion Labs there. But master students, they worked on this unfolding problem. Also, a very cute thing that this is a paper published in Duke. If you look at this footnote at the bottom of the screen, it says this paper was received by the editors of Annals of Mathematics, accepted, and then transferred to this journal. So I don't know how people would feel necessarily about having a paper accepted by the Annals and then eventually published by Duke, but I guess that's how things worked in the 1930s. A little just oddity. Publication changes all the time. This unfolding procedure was also rediscovered independently by Zamyakov and Katok in the Soviet Union, but I think it's been found by many other folks. I don't claim this is an exhaustive list. The point is it's a really cool and intuitive procedure. Let me just share with you a short video that I made partly to help raise funds for the movie about Mirzakhani. And so this is an early draft of a video created by Andrea Hale based on storyboards I shared with her. And it's going to be hard for me to listen to the voiceover. Listening to your own voice is not fun, but here you go. So you guys can't hear the sound of that?
Correct.
That's correct. We cannot hear that.
Okay. You know what? Actually, the sound is not that important, and this is great. You don't have to hear my voice, so I'll do a little voiceover while the whole thing plays with you guys. Okay. Oh, it's not letting me. Okay, so I'm gonna have to play from the start again. So we're asking how a billiard ball bounces around a table, and we're gonna idealize this, simplify it, and generalize this. Um, so here, point mass, no friction on the table. So that's why I said air hockey might be a little bit better than billiards. And this is just illustrating elastic collisions, right? So angle of incidence, angle of reflection. And the generalization is considering many different shapes of billiard tables. And so now we're going to demonstrate this unfolding. Hold on.
Continuing straight. Instead of bouncing back in the table, we're going to think of the ball as continuing straight and flipping the table.
So now that we have sound, let me go back to this.
Continuing straight and flipping the table over the wall we hit. If you notice with the square, as you can see, after 4 hits, we get a copy of our original table. The corners are all labeled the exact same way as in our original table. If we rearrange things a little bit, moving that 4th square, you can see that we get a large square. And if you keep careful track of the labels, you can see that the inside square is all glued together, and then the left side is glued to the right side, and the top is glued to the bottom. If you do take a square and you do that, you get what looks like the surface of a donut. You first get a tube when you glue your left to the right, and then you glue the top of the tube to the bottom of the tube. You get what's called a torus. And why do I say Pac-Man? Well, if you remember when you played the game Pac-Man, when Pac-Man went off the right side of the screen, he showed up on the left, and when he went off the top, he showed up on the bottom. So instead of playing billiards and having the ball bouncing around, we have the ball going through sides and coming up the other side, and we have to keep track of that. That's a tool that makes the problem mathematically easier to analyze. It turns out that this method doesn't just work for the square. In fact, if we start with any polygon whose angles are a rational number times 360 degrees, we can carry out this unfolding process. And you can see in this process, for instance, if we start with this particular triangle, we're going to get an octagon with opposite sides glued. And when you get an octagon with opposite sides glued, if you start to play Pac-Man on an octagon, you get a surface out of that ends up looking like 2 donuts kind of fused together. But there's a special point there where there's a lot of different directions that Pac-Man can go in. We'll talk more about that in the context of curvature later on.
Thank you for letting me share that video. Hopefully my sound is still okay from my microphone. Okay. So this is the unfolding procedure, and I think this is a nice picture of illustrating that unfolding, nice video. And so now, what's the actual subject of this talk? The actual subject of this talk is we want to go a dimension up and deal with polyhedra. But polyhedra are kind of even more tricky than polygons. We want to understand general polyhedra. A big question, for example, would be, are there periodic trajectories, or is there some right notion of rational polyhedra where we can do some kind of unfolding procedure? And you might think that, oh, maybe this kind of rational angle thing would work, but it doesn't, right? So rational angles don't necessarily imply that the group generated reflections in the faces of the polyhedron is finite. I remember getting very excited. Kiran Kedlaya and a bunch of co-authors had written some really cool paper classifying polyhedra with rational angles, but it was, it was a problem because that doesn't necessarily give you finite reflection groups. You don't get this nice unfolding procedure. But there is a very obvious class of polyhedra where you can do this, which is just a prism. Take your base polygon and now extend it just by the interval 0, 1. So for instance, you see this is a prism over a heptagon, which is going to be an important example for us. So we start with the rational polygon. We make the prism just p cross 0, 1. And what can we say about billiards in the prism? Are there periodic trajectories? What can we say about the long-term behavior of non-periodic trajectories? And in this talk, the rest of this talk, we're going to focus exclusively on the long-term behavior of non-periodic trajectories. And what's interesting is new phenomenon pop up, and they're related to sort of subtle ergodic theoretic properties of the linear flow of the billiard flow on the original polygon. So of course, there's a link, unsurprisingly, between the billiard flow and the prism and the billiard flow and the polygon, but it's kind of subtle. And I want to share with you a beautiful idea of Furstenberg that allows us to kind of build this connection. And I want to introduce you to the notion of weak mixing. So let me state a couple of theorems, kind of in very loose form. There are precise statements here, but these are correct statements. They're just kind of not the most precise versions of our theorems, but let me state this theorem here. For billiards in a rational prism, for almost every choice of initial velocity, the billiard trajectory equidistributes with respect to Lebesgue measure in the prism. So what that means is you take this long-term behavior of your trajectory, you take your trajectory, you pick a random direction, you start bouncing around, and the amount of time you spend in any region in the prism is proportional to the volume of that region. Questions about this? This is our first main theorem. Intuitively, intuitively, it's again, it just spreads out evenly. Things spread out evenly. A couple of remarks. So for the cube and for rectangular prisms, you can kind of prove this with your bare hand, so to speak. There's some beautiful work by Beck and Chen for a certain class of polyhedra. I don't want to get into that full detail. They show that for that class of polyhedra for almost every initial point and velocity. Our result works for every starting point. And what our work does is it relies on building an associated translation prism and using ideas of Furstenberg and Veitch, connecting the ergodic properties of the flow on the prism to the weak mixing properties of the linear flow on the associated translation surface. And we can, in fact, characterize, so what's better about our theorem than just that statement is we can characterize the directions that do and don't equidistribute in terms of something called the spectrum of the associated linear flow on the translation surface. So remember, we took a polygon P, we unfolded it to this translation surface X of P. And we're going to do a similar thing here. We're going to unfold our polyhedron to this sort of a circle bundle over the translation surface. So here it was 0, 1. That circle bundle will sort of be R mod 2z in this parametrization, will be the fiber over the translation surface X of P. And we're going to, instead of considering our billiard flow, we're going to consider the straight line flow on the translation surface, and then a lifted flow to this circle bundle over the translation surface. So it's going to be called a skew product flow. Okay, so let me state another theorem before we get to the kind of ideas that go into these proofs. Again, this is an example of our general results. And I hesitate to promise anything. We're hoping very strongly to have a preprint up on arXiv by the middle of December, fingers tightly crossed. The problem is we just keep finding new interesting things to add to the paper. At some point, we really have to stop doing that, or at least stop insisting that they go in the paper and maybe think about writing a second one. But for right now, the paper is kind of growing, which, I've given talks about this, and I keep saying that the paper will be up on arXiv soon, and then we keep finding new and interesting things. So maybe I shouldn't promise anything. And I guess this is recorded, so oh boy. Anyway, for billiards in the heptagonal prism, there are explicit directions, and I really do mean explicit. We can tell you exactly what directions to go in the polyhedron with non-zero vertical speed, which do not equidistribute, although their projection of the heptagon does. This non-zero vertical speed caveat is needed because, of course, if you just sort of if you just have zero vertical velocity, you can just keep bouncing in one slice, and you can, of course, equidistribute in the heptagon piece without equidistributing in the whole thing. But here, these have non-zero vertical speed. You don't get trapped in a slice, but you get interesting things. And in fact, this picture of what's behind me and some of the pictures I showed you earlier are kind of illustrations of a piece of this phenomenon. I'll try and explain that a little bit further towards the end of the talk. So these pictures are related to this kind of example. Okay, maybe before I start to go into ideas that go into the proofs of these things, I'll pause for questions about the statements. Again, you're always welcome to share those on chat or via Discord. I won't necessarily be monitoring the Discord super actively. Email also works really well if you have further questions, but either, a question comes to you after the talk or later in the talk.
Can I try one, Jayadev?
Go for it, Aaron.
These directions, do they equidistribute on some subsurface or some nice thing?
They should be, they're living in some kind of interesting fractally thing. And I'll try and say a little bit more about that towards the end of the talk.
I've got
Orbit closer is weird.
I'll try one too.
Go for it.
Are the direction you're getting ready to to show them, but are the coordinate excuse me, are the coordinates that you're going to be bouncing through rational multiples of the chords of the polygon?
That's an excellent question, and I have to say I don't immediately know the answer to that. So I don't think so. No, in fact, so in fact, what they're going to be is they're going to be in a direction. So if you look at the horizontal speed, sort of in the horizontal direction, in the heptagon direction, they're going to be dense and in fact equidistributed in the heptagon. They're going to be flowing in the direction of what's called an unstable. They'll be flowing in the unstable direction of a pseudo-Nosov map. And then the vertical speeds, there'll be several vertical speeds over this horizontal direction that can be that will not be equidistributed, and those will all be living in a certain number field related to the expansion factor of that pseudo-Nosov map. I don't think it's as obvious as reading off the chords, but it's certainly very closely related to the flat geometry of the heptagon. So I have to think about what the relationship to the chords of the heptagon is, but it's not exactly in those directions because those directions don't in fact equidistribute on the heptagon surface if you have a chord. Pierre asks if those directions are dense, if they're not equidistributed. No, in fact, these are non-minimal directions. These are in fact non-minimal directions. These, for the experts in the room, maybe for Pierre, these are continuous eigenfunctions. These correspond to continuous eigenfunctions on the surface. Okay, great questions. And I think, by the way, there's a
maybe
lot.
This question has been asked, but is the vertical component of the trajectory in some way irrational, in a rational ratio to the height?
No, well, the vertical component of the trajectory is going to be living in something very closely related to the ring of integers in a number field. And that's related to something called the expansion factor of the pseudo-Nosov in that direction. So they're explicit in the sense that they're living in this number field. I can tell you exactly what they are. And yeah, that's maybe the best I can say.
All right.
Maybe one more. You mentioned velocity a few times, and I'm not half the mathematician I suspect most people are here, but my picture of this, when you describe the air hockey table, is that they're going to be a uniform velocity, and so velocity is insignificant to the path. How does velocity matter?
Oh, that's your initial direction, right? Your velocity is it's your initial direction.
Okay.
Your initial
direction.
direction.
So it is direction, but it's not magnitude. It's insignificant.
Yeah. Okay. Now this is very.
I got you.
No, but this is an excellent point you're raising here, because now that we're working in this polyhedron, in this prism, we're in fact, the easiest way for us to think about this is we're going to normalize the horizontal speed, the speed in the sort of the horizontal direction. We're going to think of moving that at speed 1, and then we're going to think about different possible initial velocities in the 3-dimensional thing.
Gotcha.
By adjusting the vertical speed.
All right, that makes sense.
Yeah, and that does tend to the vertical speed relative to the horizontal speed, that's changing your direction, of course, right? So, and different vertical speeds over the same horizontal speed. When I said there are different vertical speeds, so when we fix this horizontal speed in a particular direction, there's going to be a whole group of vertical speeds, and it's going to correspond to something very close to the ring of integers in a number field, such that any of those vertical speeds over that particular horizontal direction will give you non-equidistributed directions in the prism.
All right, that's good. Thank you.
Of course, thank you for that. That's an excellent clarifying question. Okay. I think that's right, Pierre. I think that's right. So these orbits are dense, but yeah, I think that's right. Okay, let me now say, I want to give people, I know this is not necessarily an ergodic theory crowd, but I would like to give people a little bit of beautiful ergodic theory and an idea of Furstenberg. So I'm going to try and do this as quickly as possible, get to the idea as quickly as possible. So we're going to have a measure space, x mu, which is a probability measure space. So this is a space with total measure 1. And we're going to have a flow, which is just, you have for every real number, you have a map, and those maps compose in the way you think they do. Phi t, phi s is phi s, phi t is phi s plus t. And we say that this flow is called ergodic if every invariant set, if you have a set that's invariant under the flow, it should be measure theoretically trivial. Either it's measure 0 or measure 1. The total space has measure 1. An amazing theorem is the pointwise ergodic theorem, originally proved by Birkhoff, which says that if you have an integrable function and you average it over an orbit, then it converges for almost every starting point to the average of the function over the space. So you often hear this said as time averages converge to space averages. This is a beautiful, beautiful theorem. This is an equidistribution theorem, right? It says that the amount of time an orbit spends in any region, if you take f to be the indicator function of a region, is the measure of the region. And it's an incredibly powerful theorem. Now, there's also a notion called weak mixing. Let me state what weak mixing is for a flow. Weak mixing says, suppose you take two nice sets A and B, and you flow A along. So you sort of flow A along, and you see how much of it lives in B when you flow it along. And then you average that over the first big chunk of the orbit. Then that should converge to the measure of A, measure of B. That is, in some kind of Cesaro sense, an average sense, the sets A and B become what we're going to call asymptotically uncorrelated or asymptotically independent. Strong mixing is when you don't need to do the extra averaging. When you say, oh, you just take A, you spread it around, and it converges to the measure of A, measure of B. Now, a general illustrating challenge, and this is very open-ended, it's something I'd love to talk to people about in August and then again next year at IHP, is a really convincing illustration of the difference between weak and strong mixing. And let me this is very vague and very open-ended because there's lots of different kinds of dynamical systems, and there aren't that many great examples of things which are weak mixing but not strong mixing. But in particular, this world of flows on translation surfaces and a related kind of discrete map called interval exchange transformations provide good examples of flows and transformations which are generically weak mixing but are never strong mixing. They're never strong mixing is a theorem of Katok's, but they're generically weak mixings is kind of a theorem of Avila and Forney's. How do we illustrate this convincingly, that they are weak mixing, but they're not strong mixing? I don't know if there is a good answer to this, but I'd love to think about it with this community. So that's a challenge that I want to throw out. Okay, moving quickly on from that. Here's an amazing thing about weak mixing is you can detect weak mixing via something called eigenfunctions. Now, there's some lies on this page, and so for the experts of the room, you don't necessarily we can worry about these lies a little bit later. Remember, we said things were weak mixing, that if you sort of in a Cesaro sense, any two sets became uncorrelated. What's kind of amazing is you can detect this using something called eigenfunctions for the flow. A function we call an eigenfunction if it transforms in a predictable way under the flow. So I'm writing it in kind of an additive way. If you exponentiate it, then it looks more like an eigenfunction. Before you move along the flow and you multiply by something. Imagine exponentiating this equation. But this is what's called an additive eigenfunction. And what's amazing is that the flow is weak mixing is if you have no non-trivial eigenfunctions. Maybe I should say that the flow is ergodic if 0, the only eigenfunctions for the eigenvalue is 0, are the constant functions. So the only invariant functions are constant. That's ergodicity. Weak mixing says you have no non-trivial eigenfunctions. So other than the eigenvalue 0 and these constants, there's no functions that transform in this predictable way under the flow. Okay. And now, remember I said that we were going to think about our flows as flows. So when the flow on the prism is we're going to flow on the bottom, but then we're also going to flow on the top in the vertical direction at some speed. That is, we're going to consider this kind of circle bundle over my surface, and we're going to flow on the circle factor at a constant speed. This is what's called a skew product flow. So very generally, I could have a probability measure preserving flow, and I could make a circle bundle over my base space. And I could take a skew product by say, I'm just going to flow on the base by my flow, and I'm going to flow in the circle fiber at a constant speed. And now, if I'm interested in ergodicity of that flow, I'm interested in the existence of invariant functions. So suppose we had some kind of invariant function. Well, an invariant function would look like this, right? It would have to satisfy f of xs equals f of phi tx, s plus st. Now, for any fixed x, what we're going to do is we're going to expand the second function f in the second coordinate. We're going to think of x as fixed, and we're going to expand to the function in the second coordinate a Fourier series. We're going to write it as f of xs as summation cn of x e to the 2 pi ins. And then we're going to write down what it means to be invariant and set Fourier coefficients equal to each other. And if you do that, you get this equation that the function cn essentially is, now I'm writing this in this kind of multiplicative notation, Cn becomes an eigenfunction for the flow phi t with eigenvalue n times c, or negative n times c, where c is the skewing speed. So the point is, non-constant invariant functions for the skew product correspond to eigenfunctions for the base flow. If n times c is an eigenvalue, c is the skew speed for the base flow, the skew product flow with skew speed c will be non-ergot. That's kind of what underlies all of our results. In particular, if our base flow is weak mixing, there are no non-trivial eigenfunctions, then we can say for every vertical speed over that base flow, we're going to be spreading out evenly. So there's a huge number of results we can harvest from the theory of weak mixing of translation flows. Results of Avila and Forney, which say results for, in a very precise sense, almost every translation surface. Of Avila and Delacroix for what are called lattice translation surfaces. These are translation surfaces with a high degree of symmetry, which actually many of our billiard table translation surfaces turn out to be. And very recently, results of Arana Herrera, and I should be clear, Arana Herrera is one person, Chaika and Forney are two different people, so the three of them work together on characterization of weak mixing on translation surfaces in terms of what's called something called the tautological plane. And all of these, their beautiful, strong results give us really cool corollaries for linear flows on translation prisms, and in fact give us further corollaries for billiards that fall into these particular cases. I don't want to go into technical details there. I know I'm getting close to the end of time, so let me just say this quickly. Our other result is based on the idea on an explicit construction of what are called non-weak mixing flows on translation surfaces in directions corresponding to expanding or unstable directions for pseudo-Nosov maps. Pseudo-Nosov maps are maps that stretch the translation surface in one direction and contract it by the exact same amount in a transverse direction. And the particular examples we look at have to have an expansion factor, which is what's called a Pissot number, which is a very precise Diophantine condition on the number. It says the number is not, it's actually, it's a number, it's an algebraic number, all of which has absolute value greater than 1, and all of whose algebraic conjugates have absolute value strictly less than 1. This result that we prove is actually kind of a geometric generalization and sharpening of the work of Solomiak on substitution systems. And the pictures we showed at the start are level sets for eigenfunctions for examples of this type on the 20gon and on a staircase surface associated to billiards in the heptagon. And the 3D print is of an eigenfunction on the heptagon. Precisely, our theorem says the following. It's a lot of words, but let me read it out because I think it's nice. And it's actually, this is after and very much inspired by work of Pierre Arnoux in a very particular genus 3 surface from 1988 and work of Solomiak. The linear flow in the unstable direction of a pseudo-Nosov map is non-weak mixing if and only if the expansion factor is Piso. And if the expansion factor is of Piso of degree D, the group of eigenvalues has rank D. And the linear flow and the groups and the pseudo-Nosov map can be simultaneously semi-conjugated to a linear flow and a hyperbolic, not total, but toral automorphism. Excuse me, that's an autocorrect error there. On a D torus on a real D torus via the action on an invariant subspace of cohomology of the surface. So what I would love to do, and I'd love to talk more about this, obviously this is way too quick to really get a handle on this at this point, is to convincingly illustrate the semi-conjugacy in the rank 3 setting and illustrate the corresponding rho Z fractal. There's a beautiful connection to the rho Z fractal. Pierre was studying the Fibonacci substitution. And in fact, let me conclude this with an incredible picture. This is from 1988 in Pierre's paper of kind of, this is, I would say, a very convincing illustration of this conjugacy in this setting, and I'm very happy to talk more to people about this down the road. So let me stop here. I realize I'm right at time, maybe a little bit over. So let me stop here. Thank you.
Thank you, Jayadev. I wonder if folks have any questions. There was a comment at the beginning on the chat that said, these remind me of rho Z fractals. I think it was on the sort of 3D printed kind of piece with the rough surface. So I think David Hall posted that, and I was curious if that connection worked for that particular piece.
Yeah, so which figure, Saul, would you like me to show again? The 3D printed one?
I think that's what it was. David would know better.
Yes, that's the one I was referring to when I posted that.
Absolutely. So let's go back to the 3D print here. So again, full amazing work by Pat Hooper there. Yeah, so what this is this is sort of a print by height of an eigenfunction. You can see it sort of increasing steadily on the directions of this linear flow. In that particular, you can see what the direction is, and you can see kind of, all of those lines have kind of the same slope. And then when you fit it, actually, it's on the double heptagon. When you fit it together with this other heptagon printed, you can see it really nicely that this actually does fit together. And what actually is happening here, the semi-conjugacy that I talked about, is the resulting surface here is genus 3, and the pseudo-Nosov map here, the expansion factor also is a Piso number of degree 3. And so in fact, in this case, the invariant subspace of cohomology. So cohomology here has dimension 6, 2 times G, and there's an invariant subspace which is preserved by the induced action of the pseudo-Nosov. And the flow in this direction can be conjugated to a straight line flow on that 3 torus, and the pseudo-Nosov can be conjugated to the action of an integer matrix on that 3 torus with eigenvalue, the same eigenvalue as the pseudo-Nosov, as this particular Piso number. And this is a picture, so Pierre developed this picture for a genus 3 surface, known now as a first example, what's called an Arnould closed surface, and he developed the semi-conjugacy. And then what happens is if you look at the transverse direction to this flow, that's now going to live in kind of the stable space of this hyperbolic toral automorphism under this conjugacy, semi-conjugacy, and then you can kind of move along the stable leaf and you can kind of trace out this interesting path, and that's going to be what this rho Z fractal is. Pierre, please correct me if I'm saying things that are not quite correct here, but I think I'm trying to say things in sort of with an economy of words. What Pierre has drawn is he's drawn there the plane in his 3 torus. He's kind of unwrapped this plane, which is wrapping around actually densely in the 3 torus, but he's unwrapped the plane and he's drawing a one-dimensional trajectory in that plane.
Ooh.
Yeah, and so hopefully there should be cool one-dimensional trajectories and planes. There might be some choices involved, but I would love to see what those things look like in this.
Are there any other questions?
So can I ask a question to maybe people in the audience? Because I know there's some three manifolds people in the audience. Does this ring any bells for three manifolds people, right? I'm doing a flow on a circle bundle over a surface. In particular cases, this particular examples we're looking at, we have a pseudo Nosov. So this circle bundle, you know, this is a trivial circle bundle, right? Over this, I'm just taking the product of the circle. But so it's not the circle bundle that, you know, you get a hyperbolic thing on when you take the pseudo stuff. But I don't know, does this ring any bells for three manifolds people? It's a very open-ended question. Not one that needs an immediate response either.
There was a question in chat that I don't know if it was addressed or not, but are orbits that are dense still equidistributed?
So okay, so there are examples of linear flows over translation prisms. Not in these pseudo-Nosov directions, but in other directions. This is coming now from a construction of Avila and Delacroix, where you can have dense orbits in translation prisms which are not equidistributed with respect to Lebesgue measure. You can have minimal non-uniquely ergodic directions. The examples we are constructing here in these pseudo-Nosov directions are in fact non-minimal. These associated eigenfunctions are continuous. But using work of Avila and Delacroix, we can build minimal non-uniquely ergodic directions in translation prisms as well. But they're not expanding directions for pseudo-Nosov maps.
I wonder how the density field looks like for those.
Great question. That's a great question. I mean, that is much less constructive in the sense that I don't exactly know. I mean, I couldn't tell you, for instance, what the coordinates of one of those directions are. Here I can tell you. So, you know, they exist, but I don't know what they exactly look like.
Are they sort of most of the time it's like this, or are those instances rare?
No, most of the time, in fact, right, for almost every direction, you are in fact, for almost every direction, you are in fact uniquely ergodic. You equidistribute, right? Lebesgue is the only preserved measure. So this is a very atypical set. So you could ask all kinds of questions like what's the Hausdorff dimension, et cetera, et cetera. But yeah, this is a very it's a small measure set. The non-minimal, the non-ergodic. It's a zero measure set.
Great. Well, thanks so much again, everybody, for coming, and Jayadev and our show and ask speakers, Sean and Robert. Before signing off, I wanted to say that the Illustrating Math website is back up, so I don't think you should get that error anymore if you want to click on it. And Aaron, would you like to close us out?
Just to echo those thoughts, thank you, Jayadev, for bringing the joy and the challenges, all the speakers for your questions and your thoughts and sharing your work. And thank you all for coming. And I invite everyone over to the Discord for further chat. I will stop the recording and adjourn this meeting. Hope to see you next month.
Bye.
Bye, everyone.